So if we see a nonlinear pattern in the residuals from the linear model, then we might fit a nonlinear model. So what we can do then is to just make a transformation of one or more of the existing variables such that we can capture the nonlinearity in the data. So we, instead of fitting a linear model to a nonlinear set of data, we just transform the data such that we can use a linear model. Okay, so this is after the transform. Okay. So we have two common types of nonlinear transformation, and that would be the polynomial. Okay, you have the square of a variable would fit either like a concave set of data or a convex set of data. The cube, it could fit something like this or something like this, like a sigmoid curve. And the way you just make this data or this new variable is to in Stata you just type generate to generate a new variable, and then you provide a new variable name, x2, and a new value for that variable. Okay, new value. Okay, and you also have the natural logarithm, which is widely used in economics. You just type generate ln x, for example, if you want to call it ln x, and you just put the value of the natural logarithm of x into that variable. You can also do this with the y variable. And now we have to talk about the natural logarithm, because what is the logarithm of a number? The natural logarithm revolves around e, which is Euler's number, and it's around 2.7. Okay? Sorry. And the natural log of x is the exponent to which Euler's number must be raised to produce x. Okay, what does that mean? So what you have is that if you have ln of x equals y, then you have to think, okay, what number do I have to raise e to in order to get x? Okay, so this is really the exponent to get y. Okay, so the ln x is really an exponent. Okay, so and that's why you have e to the ln of x is just x. Okay, and some examples, we have that ln1 equals 0, and what does that mean? It's what is the exponent you have to raise e to get 1. Okay, and from high school math, you know that e to the 0, or something raised to the power of 0, equals 1. Okay, And here you have the natural logarithm of e. So what do you have to raise e to get the number of e? Well, anything raised to the power of 1 gives you that anything, right? So e to the power of 1 equals e, okay? Which is, it's the same as 2.7 to the power of 1 equals 2.7, okay? And the logarithm of 10, for example, is about 2.3. So this means that e to the 2.3 gives you approximately 10. Okay? So whenever you see a logarithm, think exponent. Okay? Think, okay, this is what is going on top of the natural number, okay? 2.7 something. And what does this look like? So we have here, we have origo, and we have 1 here, and let's make the 1 on this axis quite high, okay? Okay, so we see here that if you have x equal to 1, then the logarithm of x equals 0, okay? So we have a point here. And if the logarithm, or if x is around e, which is 2.7 something, then the natural logarithm of this number is equal to 1. And if you have x equals to 10, then the natural logarithm is around 2.3, right? So you have this concave function, which is ln of x, okay? And a quite useful thing, for the lack of a better word, or feature of natural logarithm, is that it's quite easy to calculate percentage differences. Okay, so for example, if x is 1, then the natural logarithm of x is 0. Okay, and if x is 10, then the natural logarithm is 2.3. Sorry. So if you want to go from 10 to, let's see, I can switch this, from 10 to 11, what is the percentage change, right? And what you would traditionally do is you take 11 minus 10 divided by 10, okay? Which gives you 10%, okay? But if you use the logarithms, then you can say, what is the change between the logarithm of 10 and the logarithm of 11? So, and the logarithm of 10 is 2.3, and the logarithm of 11 is around 2.4. You have that from this table, and then you can just take 2.4 minus 2.3. Let's see, should have taken 10% here. Equals 0.1 equals 10%. Okay? So instead of dividing, you can just subtract, okay? And for example, if you want to go from 100 to 110, then you do the same. Minus 100 divided by 110 equals 0.1 equals 10%. Okay, that was a bit cluttery. But with logarithms, you can just take the difference, okay? So the difference is 4.7 minus 4.6, which is ln of 110 minus ln of 100 equals 0.1, which equals 10%. Okay? So natural logarithms actually gives you an easy way to calculate relative differences. So, what kind of transformation should you use? Okay, what kind of transformation? That's the question. And to help us, we have Tukey's bulging rule. Okay, and here you can just plot the x versus the y, and based on the pattern you get, you can choose a transformation. For example, if you have this concave downward sloping pattern, then you can raise the y variable and the x variable to the second power to get a linear relationship between the x squared and the y squared. Okay, so and for example, what transformation should we use in the cat food example? And if we go back to the cat food example, we see that the relationship between average price, which is the x, and sales volume, which is the y, it's fitting this downward sloping convex pattern, and a downward sloping convex pattern is down here. We have ln y and or ln x, so we can choose to transform the y variable, the x variable, or both. Okay, so what we choose here is that we just take ln of y and we take ln of x. Okay, and from this either or and or, we get three different possibilities, okay, of the logarithmic transformation. We can either, as we chose in the previous slide, we can take the log of y and the logarithm of x, and then we get a percentage difference and the percentage difference. So here we say that, well, a percentage difference in price gives us a percentage difference in the sales volume. Okay, so this is actually defined as the elasticity. So the elasticity is, per definition, the percentage change in y given a percentage difference in x. Okay, and often we say that for a 1% difference in x, what is the percentage difference in y? But you can also just take like a log linear relationship. Then you have like a percentage difference in y is explained by like a unit difference in x. For example, the unit can be cans or euros. So then if you think that the logical relationship should be, well, for a unit change in x, then we have a percentage change in y, then you should use the log linear model. And the linear log model is when you take the percentage change in x should be associated with the unit change in y. Okay, so it's really just based on the theory that you choose which model you're looking at. Okay, and we're going to go through an example in the next video, and see you then.